One thing that I like to do is do a kind of an overview of some of the growing seasons, because it really seems to have a big impact on the data that we see at the lab. So we'll do a overview to get some data in context. The top of these pages here is the growing season moisture, May, June, July, and then in the bottom row is August, September, October, showing a percentage of long-term average precipitation. And there in fall of 2019, I guess for phosphate, potassium, sulfur, I'm only going to focus on 3 years of data, and for nitrogen, 5 years of data. Well, I'm going all the way back to 2019, and we had the harvest from hell, trying to suppress that memory, but it did have a big impact on what we were seeing in the soils. And fall of 2020 was a polar opposite year, and what we were seeing at Western Ag was very different sets of data, and I encourage you to think back, for those who are conventional soil testing, what were you seeing between those 2 years. Then we had the drought to 21, followed by moisture coming in August for a lot of the prairies, not everywhere, however, but we had moisture ending the drought. Moisture carried over into 22, followed by a very dry fall. And the dryness of fall in 22 carried over into the growing season of 23, with moisture coming or beginning in August in a lot of places, more in September and more in October. The analysis that Western Ag uses is the PRS probes, plant root simulator probes, and ion exchange resin membrane. When placed in the soil, it measures bioavailable nutrient supply as a supply rate over time. For consulting purposes to farmers, we collect soil samples, bring those samples into the lab, and under standardized conditions of time, temperature, and moisture the probes are in. And then that data gets interpreted by our crop simulation model, the PRS Cropcaster, that allows a farmer to, enhance his decisions, looking at different cropping scenarios based on moisture or growing degree heat or economic scenarios, looking at nitrogen. And on this graph, which is the provincial, the aggregate, we've got hard right there. Again, anything left of the gold circles, we're making nitrogen recommendations. The drought year of 21 is standing out. And I want to emphasize in these numbers, particularly with nitrogen, there's certainly residual nitrate that's in the sample or in the data, but it's also the mineralization potential of the soil. It's a combined data that is measured by the PRS probes. Now, to split that up into a regional basis, this is how I partitioned up the province. It's approximately what our franchise regions are, and I divided the Northwest region into kind of the dark brown soil zone, separating it from the black, because you have the environmental considerations that are a little bit different. I thought it's worth teasing that out. So beginning with the Southwest region, here's the pattern, and going back 5 years. So the 2019 year is evident there, where we had a higher frequency of fields that were low in nitrogen supply potential. 2020 is probably a kind of an average year, and then we had the drought year of 21, a dry fall of 22, and then the dry conditions again in 23, with a similar type of fields with very high nitrogen supply potentials as the drought year 21. 39% of fields being insufficient for nitrogen in the Southwest. The Northwest, so the dark brown area in the Northwest region, same type of pattern, 2019 being low and 2020 kind of maybe being an average, and then we had the drought year of 21, dry fall of 22, and then dry conditions in 23. Again, in 21 and 23 is when there was moisture in August and early September that was triggering a mineralization burst that conventional analysis would recognize. In 20 and 22, it has trouble seeing that as a nitrate-only analysis. Looking at the black soil zone in the Northwest, same kind of similar pattern moving into the Northeast. in the deep, rich black soils, the drought year of 21, the first one really since 1988, it stood out. This fall, we weren't quite as high, but again, the type of conditions are showing that there was a good, strong supply potential. And then what I've been seeing in southeast Saskatchewan, where I do my work, really the last 4 years have been fairly consistent. Strong falls, the dry conditions in the falls causing mineralization bursts that we're able to see at the lab. It's how we analyze the soil, especially when the soils are dry. There's an extra procedure that we apply, and in essence, what we're triggering is the Birch effect under controlled conditions. By no means do we profess to be perfect at it, but we do seem to give a pretty good indication of what the potential is. Not accounting for this nitrogen that would come into the environment can have some implications. And so what are those implications of excess bioavailable nitrogen? Well, something that isn't talked about as much anymore because our varieties have evolved, semi-dwarf characteristics, particularly in our cereals. We can have poor grain fill for a couple of different reasons. We have reduced harvest speed and challenging residue management because of excess nitrogen. Haying off is more of a circumstance that happens in the brown and maybe the drier parts of dark brown soil zone. But that's where the crop, I guess if a growing season is like a marathon, haying off is like the crop starting a marathon as a sprint and trying to do a sprint the whole season. And it has a lush, excessive lush growth early, and it's using up the water, and it just isn't available to finish out the crop. And just a couple of examples here. This is from a colleague, Carmen Watson, from near Hodgeville in southwest Saskatchewan, a little bit east of Swift Current. Her farm is in the middle of that canola field there, and looking across, and June 29th, and not a month later, her farm is in the background there, but they hayed off this year. It wasn't even a month. They had good moisture. They had fantastic germination, but there was no moisture to depth. Here's an example from Bull Island a few years back, a very dry year, 2018, and comparing a fertilized barley versus zero fertilized barley. That looks different, but the 0N barley yielded 68 bushels an acre versus the fertilized barley yielded 56, and there's evidence of haying off. There can be ammonia emissions right out of the plant. This is a small consideration, but 1 to 4% of nitrogen can evolve right out of the plant leaf, and the tendency is to increase when nitrogen concentrations are high. This is a heat map that shows the left-hand side is where normal nitrogen applications were made. Right-hand side is where excess nitrogen is applied. And I apologize for how small it is, but there's over 80 metabolites being listed there. And it's basically a graph showing how the physiology of the plant has been impacted by excess nitrogen. And basically the excess nitrogen is inhibiting and I always stumble over this. It's the antioxidant. It suppresses antioxidant production in the plant, and it disrupts physiology. What can that impact? And I shared this last year, as if there's too much nitrogen in the system, well, you can impact yield ultimately. And in this case, it was over 8 bushels an acre, or $160 an acre reduction in yield potential. And finally, with the environment, if there's excess nitrogen in the environment, there's a nitrate exposure, there's very good correlations that increases our nitrous oxide emissions. And that's been a big deal here from a federal perspective, trying to encourage farmers to be better stewards of the nitrogen that they use. And so to wrap it up, from my perspective, the priority to meet aspirations, either economic or environmental, and for all the conversations that we've been having with 4R nutrient stewardship, right source of fertility, right time at the right place. From my perspective, the most important is the right rate. Thank you.